Hello, everyone. Thank you very much for the invitation to give this talk. We'll try this talk to give you a flavor. Went straight to the end. This is possible. This goes around. Try to give you a flavor of the work we are doing at the Aristotle Research Center at the European University Cyprus on astrophysics. It's a combination of work in astrophysics and machine learning, data science, and generally computer science. Okay, I will start by, I appreciate the audience here is not very have much background in astrophysics, so I try to put out some basic stuff first. And I'll start with what some of the current challenges in galaxy evolution. You know, galaxies did not, in the past, didn't necessarily was the same as the galaxies at present. So in this sense, we talk about galaxy evolution. So we are interested, first of all, to understand galaxies, of course, consist of stars. We're interested in how galaxies form their stars in the history of the universe. Some of the processes were different in the past compared to the present. We are also interested, galaxies also have at their center supermassive black holes, which are clean material, and they can emit more energy than the galaxy itself. They generate the phenomenon known as quasar, probably 100 times as much energy as a spiral galaxy like our own. So I'm interested in the history of how material is accreting onto supermassive black holes. Another important phenomenon is the effect of feedback. We believe that the history of the universe, black holes have an effect on star formation. This is something which is required by models of galaxy formation. I'll give you some more details in a minute. There's a lot of interest in a plot known as the star formation history of the universe, which gives you the rate at which the universe as a whole was forming stars in its history. One important question is, there are various cosmological simulations which take a lot of time actually to compute, and you require big supercomputers to run them. A big question is, do the results that come out of these simulations, which take into account most of the physics of galaxy formation and evolution, do they agree with the observations? That's another important challenge to answer. And I would like to say that to do progress here, clearly need to gather and interpret information from the spectral distributions of galaxies. What is this? We are interested in how the energy emitted by galaxies is distributed over the spectrum. We are interested, galaxies emit all the way from the X-rays to the radio, and it's important to gather information at all of these wavelengths in order to understand these processes of galaxy formation and evolution. In this talk, we will mainly concentrate on the part of the spectrum between ultraviolet and millimetre, still 4 orders of magnitude in wavelength. Okay, so I move on to this slide here to make a very important point that in astronomy, in astrophysics, we usually look at images like the galaxy on the left, which is a famous radio galaxy, nearby radio galaxy, known as Centaurus A. You can see very nice spectacular pictures here. You can see the disk with patches of obscuration. You can see 2 radio jets emanating from the center, which indicate that there is a supermassive black hole in this galaxy. Okay, images are nice up to a point. They give you a picture of what the galaxy looks like, but in order to study the physics of galaxies, you actually need to look at pictures like the one moving in the wrong direction. Sorry. To make progress in understanding the physics of galaxies, you need to study plots like the one on the right, which is a plot of the spectral energy distribution of this galaxy. We modeled the SED of Centaurus A back in '99. And to do this, the curves are various models for the emission of different bits of the galaxies. The blue arrow, for example, indicates the emission from an AGN torus, which is associated with the active galactic nucleus, the accreting supermassive black hole. The red arrow indicates the emission of recent star formation in the galaxy, something we call a starburst. And the orange arrow indicates the emission of the host galaxy. You need to have models for these different components of galaxies to be able to interpret the spectral distributions and estimate quantities like the rate at which this galaxy is forming stars. What is the mass in stars overall? What is the ratio of the luminosity which is due to accretion and star formation? And we have methods for estimating this quantity, as I'm going to show in a minute. Okay, moving from a galaxy which is in our neighborhood, Centaurus A is only 4. Here I show a similar two pictures, the images on the left and the SED on the right of a very distant galaxy, now at redshift 4.3, which we discovered in a survey called HELP, in a project called HELP I'm going to talk about later. Okay, the galaxy is the thing in the middle in these 6 postage stamps. Very hard to see. Sorry, I keep losing my, probably this thing is programmed to move. Very hard to see any galaxy in this, but I assure you there is a galaxy there. And on the right, we feed this galaxy, the SED of this galaxy by the models I'm going to describe later in this talk. And we find that is dominated by a supermassive black hole indicated with a blue line here. And there is a lot of star formation as well. So the kind of game we want to play in this field, we are playing as a group at the Aristotle Research Center, is to study the spectral energy distributions of galaxies and interpret them and infer the nature of the galaxies and study galaxy evolution. Here you see, I talked about an AGN torus. It's a structure that is believed to, in this thing here, works. Yeah, okay. This is the supermassive black hole around which there is an accretion disk, which generates most of the energy, the primary energy of the system. Around this system, here, the yellow and magenta clouds here, is what we call an AGN torus. And all of these phenomena associated with the supermassive black hole are called active galactic nuclei, or AGN. These may be clumpy, they may be smooth. We don't really know because we are not able to resolve this thing very much. It's only about the size of a solar system. If you look at the cosmological object at a fair distance, there's no way you can resolve to see this. So we are trying to infer the nature of this region here around the supermassive black hole by fitting the spectral energy distributions of objects we suspect there is an AGN. Okay. This is another famous diagram in galaxy evolution, which plots the star formation rate of galaxies, the rate at which they are forming stars, as a function of the stellar mass of the galaxies. It's a diagram called the main sequence. That is believed to be a main sequence of galaxies that is indicated by the solid line here. There's a lot of scatter, of course, but according to this diagram, the idea here is that galaxies generally in the universe, they sit on this so-called main sequence, they keep on forming stars. Whenever, however, there's a merger, because galaxies usually have, they interact or they merge with each other. Whenever we have the phenomenon of a merger, we have an elevation of the star formation rate. And we have these things called starbursts here, which can be 10 times above the main sequence. Understanding this diagram is very key for in astrophysics, in galaxy evolution. And of course, to estimate quantities like this, star formation rate and stellar mass, we need to fit the spectral energy distributions of galaxies with models to estimate them. This is the only way to get them. And there is clearly a lot of uncertainty in these quantities. Here is a diagram which I'm trying to make the point that there is a lot of the phenomenon of feedback in galaxy evolution. According to cosmological simulations, in order to have the right the luminosity, so-called luminosity function or stellar mass function of galaxies, you need two types of feedback from star formation or supernovae at low halo masses and AGN at high halo masses. And this a prescription for how the AGN, once it is energized in a galaxy, affects its surrounding and switches off star formation. This effect is incorporated into simulations of galaxy formation. And it's something that observers are looking for. They're looking for evidence that this thing actually happens in practice. Okay, another famous plot, as I said, is the star formation history, the plot of the star formation history of the universe. Here we are looking star formation rate as a function of Z, the horizontal axis, and look back time at the top. So at redshift 0, we are looking at the very near history, the recent history of the universe. We understand what is going on up to redshift 2 fairly well, but beyond that, there's big uncertainty, obviously, because you need to detect galaxies at high redshift back in time to be able to estimate the rate at which they're forming stars. You see the big uncertainties here, the big error bars. This is an old figure. On the right, it's a very recent figure by Baroufet et al., which still there is quite a lot of uncertainty. The diamonds, the red diamonds here are actually data from the James Webb Space Telescope, which discovered a lot of galaxies, so-called HST dark galaxies, galaxies that they were not visible with the Hubble Space Telescope, and now they are visible with the James Webb Space Telescope. And there's a very big area of research now, big programs being undertaken to quantify what is the star formation rate at redshifts 5, 6, 7, up to 10, to characterize better this curve here, which is important, of course, to compare with models again. Here, okay, I return to the point about cosmological simulations. There are very big simulations. One major problem here is that these cosmological simulations, they only give you mainly the mass. You start with dark matter halos, which you merge and so on. They usually give you the distribution of, tell you about the mass of the stars, the mass of the gas, and so on. You need to have a post-processing step of converting the mass into radiation so that you can compare with observations. It's not an easy task because you need to take into account the geometry and so on of the galaxies. And there is an attempt, a couple of attempts, the most important of which is this one by Camps et al. 2016-18. They post-process the results of the EGOT simulation, of the major simulations, and I'll show you later some of our own work on trying to do something like this. Now, why do we need, so let me answer the question, why do we need to study? Why don't we just observe galaxies in the optical UV and that's it? We can study them and understand them. The reason we cannot do this and we need observations and models for what galaxies, how galaxies emit, at least from the UV to the millimeter, is because galaxies are full of gas, of course, and about 1% of the mass of the interstellar medium is in tiny dust particles, which are very much more efficient than in absorbing the ultraviolet and optical light compared to the gas. So you need to take into account the absorption, the scattering, and the re-emission of these tiny dust particles to understand the energetics of the galaxies. What is and be able to infer the quantities we are interested in, the star formation rate, the stellar mass, and so on. So we need definitely observations of galaxies from the UV to from 0.1, say, to 1,000 micrometers in the rest frame. Imagine, of course, that we are looking at a galaxy at redshift 10. You progressively need to move to longer wavelengths to be able to see the same radiation. And we also need models of how galaxies emit and methods of comparing the models with observations. And this is what we are mainly trying to do in our group. A very important class of galaxies which were discovered by the infrared astronomical satellite in 1983 are objects known as ultraluminous infrared galaxies, which are mainly infrared emitters. There's so much dust in these galaxies, which is mainly due to the fact that they are recent mergers between two spiral galaxies, that all of the energy, something like 99% of their energy is emitted in the infrared. IRAS was the first satellite which was launched by NASA in 1983, which mapped the whole sky at 4 different wavelengths, 12, 25, 60, and 100 micrometers, and detected a class of galaxies known as ultraluminous infrared galaxies, or ULERGs. We see here the nearest of these objects, which is called ARP220. This is a combined image of Hubble and James Webb. And it's clearly a mess. It's not something we recognize as a spiral galaxy or a spheroidal or an elliptical galaxy. It's something that is in the process of merger. And this galaxy emits about 100 times more energy than the Milky Way. And the energy is believed to be due to star formation, intense star formation, which was triggered by the merger, and accretion of material onto a supermassive black hole. There are about 100 of these objects. These objects are very rare in the local universe. About 100 to 200 of them in the local universe. But moving on, okay. This is on the left, we see a telescope called Herschel, which was launched by ESA in 2009 to 13. And one of its main aims was to study objects like this, infrared dominated objects in the local, but also high redshift universe. We participated in a survey of 42 of these local ULERGs in a project called HERUS, which was led by Duncan Farrar at the University of Hawaii. And we observed these objects in spectroscopy and photometry mode. I will show you, this one here is my favorite of these objects. You see on the left, it's a Hubble Space Telescope image. It's a merger of two. It's an early style. It's not like ARP220 where the merger is more advanced. Here it's an early stage of the merger of two spiral galaxies. We studied this galaxy called 08572 plus 3915. It's actually, for me, is one of the most interesting galaxies in the local universe, because if you do the calculations of what the energy source, what is the energy source of this galaxy, it turns out that
90% of its luminosity is due to an accreting supermassive black hole, which is impossible to see from the image. You can only see from the plot on the right, which is a model of its spectral energy distribution. And this makes it the most luminous galaxy in the local universe. Now, IRAS detected lots of these things in the local universe. We're talking about local universe, we're talking about, imagine the volume within 1 to 2 billion light years. It's still a very large volume, but it's the local universe. SCUBA, which Stelios mentioned in his introduction, is a project I participated 25 years ago. It was a pioneering telescope, an instrument mounted on this telescope in Hawaii called the James Clerk Maxwell Telescope, JCMT. This telescope made the first maps of the sky at sub-millimetre wavelength, 850 micrometers. The idea, it was designed to detect high redshift versions of the local ULERs. And in a paper in Nature in 98, we detected the first objects, one of the most 4 or 5 objects in the field called in the Hubble Deep Field, which you may have here. The resolution is very poor compared to the Hubble image, but still it was the first image of the sky at these sub-millimetre wavelengths, where it's ideal for detecting high redshift versions of local ULERs. And now there are millions of these objects known in the universe. In this project, in which we also participate at the European University Cyprus, Herschel Extragalactic Legacy Project, it combined the data from telescopes like Herschel, Spitzer, which was an American NASA mission before it, ground-based telescopes. We assembled the spectral energy distributions of more than 170 million galaxies, 4 to 6. And this provides a huge database, which we're trying to exploit in our group. Millions of these infrared galaxies to the depths of the universe. Of course, now we have the luxury to add this database, James Webb data. It's one of the projects we plan to do. Okay. Now, so far, I talked about photometry. So in astrophysics, you can take images, then extract point sources in an image. Very important in astrophysics, and something that became possible with Spitzer, a mission that was by NASA in 2003, is to take spectra of these infrared galaxies in the infrared. Here we see spectra from Spitzer from 5 to 30 microns. And this is for these averages of different extragalactic objects. And you can see a very rich spectra, which give important information, not only about the composition of the dust that is in this part, in these galaxies, but also the distribution of the dust, if you like, and the energy source which hits them. For example, with red here, we see quasars, objects that are creating supermassive black holes. The emission is dominated by the black hole. With black, we see objects called ULERs, as I mentioned earlier. You see how different the spectra are. They have this absorption feature at 10 microns compared to an emission feature by quasars. They have these features which are due to polycyclic aromatic hydrocarbons. Okay, and you see a lot of intermediate situations, Seyfert-1s, Seyfert-2s are different kinds of AGN. These kind of spectra are of crucial importance for understanding these infrared galaxies. And we are trying to incorporate this kind of data in our analysis. Okay, now, since we have all of these phenomena, we have the data. We also have models, which, as I'm going to show in a minute, which model these different effects, star-forming regions, host galaxies, accreting supermassive black holes. We initiated a project called Cyprus Models for Galaxies in their Nuclear Spectra, Cygnus, which takes a holistic approach in studying these galaxies. First of all, we develop our own models of how AGN, star-burst, host galaxies emit. We use other models which are publicly available in the literature, especially for the AGN torus, as you will see. And then we develop MCMC methods for fitting the models to data. And obviously, this methodology, this approach is very useful for analyzing data from Spitzer, Herschel, and James Webb on the right here, which we're beginning to get data from. This is a schematic of our approach. We have in the middle, for example, you see the AGN. We have the option of using 4 different models for the torus, our own model, a model from Siebenmorgen, Skertor, Fritz. Appreciate you are not don't have a background in extragalactic astrophysics, so these are familiar models in the literature. Starburst model, at the moment we use a single version of Starburst model. And for the host galaxy, we can model the galaxy as either a disk or spheroidal. Can probably skip the details of the Starburst model apart from to say that obviously here we have stars don't form out of nothing, they form inside clouds. We have a model of how these clouds evolve as the stars themselves evolve. And we have a model for how the spectrum of a starburst episode evolves with time and other parameters, the optical thickness of the clouds and so on. Here we see the model for the AGN torus, which is our own model, the Cygnus model. One thing I should highlight is that this thing here is so optically thick that it's optically thick to its own radiation. And on the right, we see the spectrum of this thing as a function of inclination. There is a dramatic difference between what you see edge on and face on. It's not just a question of obscuring the quasar, the black hole in the middle. It's also its own emission is very much dependent on inclination. This is an important thing we need to take into account when we are modeling these sources. These are examples of smooth, what we call smooth tori. These are examples of what we call two-phase tori, where you have a smooth medium and clumps within it. The left is the model by Skertor, I mentioned earlier. On the right, the model by Siebenmorgen. As also polar dust region, as dust is not just in the torus, there's probably a little bit of dust in the polar regions, which you need to take into account. And I should say a few words about our spheroidal and disk models. We have 2 different geometries here. The spheroidal is more something that you can approximate in the sphere. And disk is something more like a spiral galaxy, because we have a lot of galaxies that are amorphous, a combination of these 2. But these are the 2 approximations, if you like, we can treat at the moment. And of course, what do? We compute the radiative transfer, the emission from these structures with our codes for radiative transfer. And then we feed all of this information, the data, the models into an MCMC fitting code. This is an important novelty we introduced in our approach in the last few years. There are various methods of comparing with the data with the models. we found that we can, using libraries of models for the emission of these different components, we can fit a single galaxy in 2 or 3 minutes. And in our approach, as I said, we used 4 different combinations of AGN torus models. This is important because we want to test the different models, which one fits the data better. This is a schematic of our approach. And I'll show you some results. I don't know how am I doing with time these days. Okay, let's try to add some more detail. Okay, so now we're beginning to see some of the results of this approach. These are 4 examples. They are not as extreme as the ultra-luminous infrared galaxies I showed earlier. These are called luminous infrared galaxies. When something has a luminosity above 10 to the 12 solar luminosities, it's called a ULER. If it's below 10 to the 12, it's called a LER, luminous infrared galaxy. And here we see on the left 4 examples of these galaxies, which we carried out this SED decomposition, as we call it, and we can separate the emission from star formation region with red, AGN with blue, and with the orange, we have the spheroidal component. Using this approach now, using our SED fitting code, we can estimate things like the luminosities of the different components, the range at which they are forming stars, their stellar mass, their AGN fraction, the ratio of the luminosity from an AGN, the black hole mass, the dust mass. We can estimate the supernova rate, the rate at which a supernova are exploding in the galaxy, and this we can compare with observations. We can estimate the size of the torus, and there are now ways to compare them with observations with data from James Webb. It has exquisite resolution, spatial resolution, or an interferometer called ALMON, you may have heard, which observes in the sub-millimetre part of the spectrum. Here you see some examples of our analysis of the Hero sample of ULERs. At the top we have 08572, which is, as I said earlier, is an object we believe is very much dominated by an AGN. We see this also here in our recent analysis with blue. 90% of the luminosity is from an AGN. And on the below we have ARC220, which is the object which is dominated by star formation. You see the red line is dominating here. By the way, these are all logarithmic plots, so differences are very important in the scale. But we also detect in this object ARC220 a very luminous AGN, which was a novel result, an interesting result. Here we see a plot where we are able to compare the fits with the 4 different AGN torus models: Cygnus, Fritz, Skertor, and Siebenmorken. On the right, we see a detailed comparison to the Spitzer spectra, which are shown with green. As you can see, the Cygnus model tends to perform better. So in this way, we can constrain the properties of this obscure torus in AGN. Something, as I said, we cannot observe this directly, is by an analysis like this, we can infer its properties. There's a comparison of the likelihoods of the 4 different combinations of models. These are 2 examples of galaxies where we found evidence that we have 2 AGN tori. One we observe edge on, one we observe face on. The dotted line represents a quasar, basically, observed face on, and the solid blue line corresponds to an obscured AGN. This is an example. By the way, we have, I didn't mention, we have 2 different codes for fitting the SEDs based on an MCMC approach. We have SADMC plus, which is a code, an adaptation of a code developed by Seth Johnson and published in 2013. And we are now developing a new code called SMART by our PhD student, Aris Barnava, and here we have results from this code on a very interesting galaxy published, discovered a few years ago in the Cosmos field. This thing is at redshift 6.853. You can see how awful is the images on the right. This is so distant, this object. This was before James Webb. But there's quite a bit of data for this thing, and we can apply this same approach of fitting it with different AG and torus models and inferring the nature of the torus and the luminosity source. And we find that in all of the cases, this is an object which is dominated by accretion onto a supermassive black hole. But there is still significant emission from a starburst in red, although it's a very high redshift object. Okay, and now I move on to finally to a few applications of machine learning, which is the result of our recent work. This is work that was done during within funded projects, but also work done by our students in the Master in Artificial Intelligence. I will start with this. First of all, I think I made it clear that it's very nice that to have spectra of these galaxies in the mid-infrared from 5 to 35 microns. Unfortunately, though, for the vast majority of the galaxies we would like to study, all of these millions of galaxies in the Hell database, for example, we don't have this kind of data. So this was a project to try to see, can we use machine learning, and in particular generative deep learning, to train it so that it can give us an idea of these mid-infrared spectral galaxies. We use data from the Herschel. We use simulations of galaxies from our models for the emission of galaxies, and we try to see if we can train the system from the 20 bands or so we have in Hell from 0.05 micrometers to 170 micrometers, whether we can train the system to go from these 20 photometry points to the mid-infrared spectrum. And the result, actually, we were happy either way. If it's possible to do this, then in principle you don't need a very telescope to give. If you look at high redshift galaxies, you have to bear in mind that even James Webb cannot give you this kind of data. James Webb can observe only out to 28 micrometers, which for any galaxy above redshift 1.5, you cannot get the spectrum you want. You need a telescope which can do mid-infrared spectroscopy, far-infrared spectroscopy, which is very, these telescopes are in the planning phase. So it was very interesting to see if we can reproduce this spectra. And it's amazing that in 70% of the cases, here you see 12 examples, in 70% of the cases, we are able to predict the mid-infrared spectrum, which we find very interesting. And there's a paper describing this work we are about to submit to Astronomy and Computing. You see, you can, this works especially in objects like this, where there is a mild absorption pictures, or in cases like this, where it's a very deep absorption picture. So this is very encouraging, but obviously it cannot substitute actually going to observe these galaxies. But this approach can give you an idea of the spectra of these millions of galaxies we have in the databases like HELP, and it can also be used to plan future observations. Another approach, another application of machine learning, which we are very much interested in, is the following. Computing the radial transfer models is very computing intensive objective. We are talking about from even for a spheroidal component, the spherical model, you need 10 seconds to compute the model. If you move on to a disk, you may need 1 minute. If you want to go to an AGN torus, you may need 20 minutes to an hour. So it's not possible to use to calculate models for these components in real time as you do the fitting. This is why we use a library. One way to get around this is to use a method that it was developed by a group that are actually interested in planetary atmospheres, a group led by Himes et al. 2021. They developed a code called March, which using machine learning, you see the outline of the thing here, if you throw in lots of simulations into the system and into the neural network, you can train it to predict the spectrum in a fraction of the time you need to actually do the radial transfer calculation. So we are trying to test this. This is a result from this paper, which seems to work very well. So we are trying to do as a first step to do this. We use March to do this for the spheroidal component. Yeah, you hear some preliminary results of our work. This is coming out of the MSc thesis of our student Petros Papaleonidas on the MSc in Artificial Intelligence. Here, so we generated lots of spheroidal models, each one of which takes 10 seconds to run, 50,000 models with, we have a total of 20 parameters here, something like that. And then you train this system for about for a day, then you can make it to predict with any parameters you give it, the spectrum of a spheroidal galaxy. Here, the true and the predicted are basically identical. I just shifted the predicted by a small fraction to make it visible. It seems to work very well and seems to be very promising to apply to other geometries like this, which takes even longer to run, and other AGN torus models and so on. So this looks very promising. Another application of machine learning we are exploring, generative adversarial networks in particular, is to improve the resolution of cosmological simulations. This is a very big area. You know, as I said earlier, cosmological simulations take lots of time to compute, but there are a lot of projects at the moment where they are using GANs to produce simulations in a fraction of the time compared to the time it takes to the complete simulation. We are trying to explore this again with MSc students. And for example, I can show you here some results. Here on the left, we see there is interest here. You see, although the simulations have a certain time resolution for calculating the spectra of integrating the star formation history and estimating the spectra, it's interesting to have more resolution. So this is an example where we improved the resolution of the equal simulation using this approach. And now finally, I move on to a couple of examples, a couple of other applications of in our group, namely an application using kernel PCA to classify these Eulers, these local Eulers I talked in the beginning, 100 or so Eulers. We added about 37 quasars, local quasars, PG quasars, and we developed the diagram. This is work that is already published by New et al. Using kernel PCA, we developed this interesting diagram where you can. It's interesting that galaxies and quasars lie on this arc, this ellipse, incomplete ellipse. The yellow stuff here, you see up to 20 here, at the very edge, is one of the most extreme. It's not only the nearest of these Eulers, it's very extreme, it's very obscure, very deeply buried in dust. So we see that the very edge of this distribution here, we see at the other end of the ellipse quasars, things that are believed not so much to be dominated by star formation, but by accretion onto supermassive black holes. Things which are a combination, if you like, of deeply obscure starbursts like up to 20 to quasars like PG0049 here. And then it's interesting, we see a few cases where there are exceptions, they lie outside this ellipse, the red squares here. And one of these is 08572, the source, the deeply obscure source I mentioned, I also discussed briefly. On the right, we see another diagram from this paper, which shows the distribution in the two principal components, which we believe are associated with the strength of the PAH features and the silicate absorption features in these galaxies. So this is a very interesting diagnostic diagram for understanding local Eulers, and we plan now with the availability of James Webb data to expand this to other samples. Another application of our group is in graph theory. What do we do here? We, again, looking at these 100 Eulers, 37 quasars. What do? We compare each other and construct a similarity matrix for all of these 107 objects. And then we do a graph. We see, for example, here on the right, the graph, the red, you see the graph consists of different clusters. On the right, with red, we have deeply obscure Eulers like R220. The yellow stuff here are the quasars. And again, we have intermediate things here. So these approaches help us to understand a little bit the evolution of this population, this local population of extreme infrared emitters. Here on the left, we see this is similar to the diagram I showed you earlier from Spitzer data. You see the mean spectra. With red is the Eulers, with yellow is the quasars. We also have intermediate situations. And this is an application, a very interesting application by, I should say, this work is from our second PhD student, Orestes Pavlou, who submitted this work to Astronomy and Computing. The paper is about to be accepted. And this is work from our third PhD student, Hans Papadopoulos. He's doing something to do with graph theory as well. What we did here, we selected from the health data, big database of 170 million galaxies, 200 galaxies at redshift 1 and 200 galaxies at redshift 2 in a specific field of the sky. What we did, we fitted them with our SED fitting codes, and then we did, I remind you that for these galaxies, we don't have a detailed spectra in the infrared. So we fitted them, and then we used the best fits to do this similarity analysis, again with graph theory. It's important to say that we fitted them with the 4 different AGN model combinations we have available. What is interesting here is that, okay, this is preliminary results because Michalis is preparing a paper on this, but one of the things we are trying to see here is whether we can see any evidence for this so-called feedback in these galaxies. For example, here on this top right, we see on this graph a concentration with red of galaxies with a lot of AGN activity, a lot of large AGN fraction, but we don't really see a reduction in the star formation rate in the plot below it. So it doesn't seem to be the case that even if you have a strong AGN, that you have a reduction in the star formation rate. And this is an important result. It's confirmed that, which is generally appreciated in the community, that this so-called phenomenon of AGN feedback may not have so much impact on star formation as is widely believed. Other people who note this. Anyway, this was a summary of our results. The summary of I don't know how much time I have. Okay. Just to summarize, to study galaxy evolution, we need data from the X-rays to the radio. We don't do very much work on X-rays and radio. Concentrate on to millimetre, but those wave bands are also very important. Interstellar dust has a lot of profound effects in shaping the spectral energy distribution of galaxies. There is a lot of data, and there's a lot more coming up. For example, there's all this data in the health database I mentioned, but we can add to that now James Webb data. Euclid is the new mission that was just launched by ESA this month. It's going to be able to map the optical sky 100 times faster than the Hubble Space Telescope. It provides lots of new data for this kind of work. Although Euclid is mainly meant to help us understand dark matter and so on. Still, to do that, we assemble lots of optical data and near-infrared data, which will be useful for analysis like this. ALMA is the big interferometer in Chile, which keeps on producing new data. There is a mission planned by NASA called the Roman Space Telescope, designed to launch in a few 3 or 4 years. This is again similar to Euclid. And there is telescopes like ELT, the 40-meter telescope being built by ESO in Chile. Unfortunately, as I said, we will not have a telescope which will give us mid-infrared spectra of galaxies at Z greater than 1.5 for at least a decade. There are a couple of telescopes being talked about, no commitment yet either by NASA or by ESA. There was a plan by ESA to launch a satellite like this. Then I note here that we need sophisticated, we have available but we need to improve more, perhaps, our models for how different bits of galaxies meet, and fit them and develop methods to fit them to data. And an area which is really developing very fast is the application of machine learning and data science methods in general to help us in this journey to understand and interpret all of this data, to have a complete picture of galaxy formation and evolution. I should say that you probably heard in the news that James Webb is already producing data that challenge our understanding of the early universe. It's discovering lots of galaxies that are higher redshift 10, 12, that are too massive. People are talking about already more efficient star formation. We don't really understand very much what is going on. But all of these methods, all of this data will be useful for making progress in this field. Thank you very much.